So today I want to talk about, in some sense, the most basic problem in the cognitive variations, which is to minimize, to look at minimizers of integral functionals. So these are, autonomous functionals. And, today we are really interested in the vectorial case. So we are interested in maps, which go from a domain omega, which is a domain in Rn, to Rm. And these are really maps. So M and N are at least 2. And okay, so this is, of course, the classical problem. In the vectorial case, a crucial feature of vectorial problems is that often F is non-convex. And in fact, I will kind of try to convince you that, in some sense, convexity is an inadmissible condition in many problems. And in particular, in elasticity, you should think that F is like a stored energy function of your material, which sits in kind of a reference configuration omega, which you then deform according to maps U, and okay, minimizers will give you some model of elasticity. Of course, the precise type of material that you have influences the choice of F that you want to take. And in elasticity, it's very easy to see that the energy cannot be convex. So this is kind of a classical example. You consider an elastic rod, you prescribe displacement boundary conditions which compress it. And of course, you are in a model without gravity. Let's say you have, in 2 dimensions, you have, the rod can either bend downwards or upwards. In 3 dimensions, it can, of course, also bend sideways. So you get a full circle of solutions. Of course, all of these solutions are the same energetically. And so, you do not get uniqueness of solutions, even in almost trivial examples. So the energy cannot be convex. So kind of an example that we will look into is these kind of Neo-Hookean models, where the energy is a term of the distortion plus a term of the determinant of the map. Okay, so you can think that this is a measure of distortion of angles, and this is a measure of distortion of volumes. Okay, and so this is not a law of nature by any means. It's just, it's just an example. Sometimes people call this the additive isochoric volumetric split. This is the isochoric part. This is the volumetric part. And okay, this is kind of classical in the physics literature. It goes back at least to Florey in the 60s, and it has been studied extensively to model materials with a slightly compressible behavior. And okay, this is just an example, but again, you see very clearly that this will not be a convex energy in general because the distortion is not convex, the determinant is not convex, so this will not be a convex energy. So what is the correct convexity condition? Well, the correct convexity condition in vectorial calculus variations is quasiconvexity. And so quasiconvexity reads as follows. It's kind of a strange definition. The sine of omega times f of a is less or equal than the integral over omega of f of du for all linear maps A, all matrices A, and all maps U which are smooth maps which agree with A on the boundary. So, okay, what does this say? Well, it really says that linear maps are minimizers of your energy, right? On the left, you have the energy of the linear map A. On the right, you have the energy of a competitor. Again, U is really a competitor. It has the same boundary values as A. So that's just a definition. Another way of writing this inequality, which will be useful later, is to think of it as follows. You can also rewrite it in this form. So the dashed integrals are just averages. And, right, so the average of the U, because U is equal to A on the boundary, that's just A. So, here you have f of A, and then you divide by omega, and on the left you get the average integral of omega of f of du. So this is just another way of writing the definition. This is a nice way of writing it, because you see what quasiconvexity really is. Quasiconvexity is Jensen's inequality for gradients, right? So Jensen's inequality tells you that if f is convex, you can pull it inside the integral, whatever it is. Okay, quasiconvexity, you can do it as long as you have a gradient inside. So that's what it is. So, of course, physically it's quite natural. It just says that linear maps have minimal energy, but mathematically it's extremely natural. And so if you have growth conditions, then it's classical and essentially goes back to Morrey work in the 60s, that quasiconvexity is really equivalent to existence of minimizers in the correct space. So, it's not just a natural physical condition, it's also kind of the correct mathematical condition for existence. Yet, there is a problem with quasiconvexity in elasticity. And the problem is that here we have to assume growth conditions, and these growth conditions fail for all elastic models that you can imagine. And so it has remained an open problem since the 80s to really prove existence of minimizers for genuinely quasi-convex energies. So these are in the elasticity. So to prove existence, for energies which become unbounded in the region where the determinant goes to 0. Of course, this is kind of a natural condition in elasticity because, this is in some sense the regime where elasticity is breaking down, right? When the Jacobian goes to 0, you are having maps which map sets of positive measure to null sets. So you are getting interpenetration of matter and all kinds of things. So this is, in some sense, the theory of elasticity breaks down in this regime, and so you should expect also your energy to become unbounded. And it happens like for the examples that we saw in the previous slide. So, so what is, I've given you a definition of quasiconvexity. So what is the main example of a quasiconvex function? The main example is a determinant. So for the determinant, actually, the quasiconvexity inequality holds with an inequality. So psi of omega times the determinant of A is equal to the integral over omega of the determinant of du for all maps U which are ion boundary. So if you've never seen this before, you can just think that the determinant of du can be written as a divergence, and then you can apply the divergence theorem and you just pick up a boundary term. So this is somehow the main example of a quasiconvex function, which is not convex, right? Because if you are in any dimension larger than 1, you will have directions along which the determinant grows negatively very fast. So it cannot be convex. So in general, quasiconvexity is really weaker than convexity. And quasiconvexity implies another convexity condition, which is known as rampant convexity. So rampant convexity just means that you have convexity along rampant segments. So if you take two matrices A and B, which are, rank of B minus A is 1, so they are connected by a rampant matrix, then you have convexity along the segment A and B, right? So that's just usual convexity along that segment. So rampant convexity is just convexity along rampant lines, and it is a necessary condition for quasiconvexity. So, for the purposes of this talk, again, it's a natural condition because it's a necessary condition. But actually, it's much older than quasiconvexity. It's really an ellipticity condition on the Euler-Lagrange equation. So you can think about it as a kind of a regularity condition on critical points. So, so of course, when you see an implication, you usually like to ask whether you can reverse it, and this is what Morrey did in the 50s. So, give me a rampant convex function. Is it quasiconvex? And at this point, even without knowing the answer, you have to realize that if the answer is in any way true, this is probably one of the most beautiful things in mathematics. And the reason is the following. These two notions are notions from different worlds. Rampant convexity is a condition which, in some sense, is trivial to verify, right? This is a calculus condition. If you give me a smooth function, how do you verify if it's rampant convex? You take two derivatives along certain directions, it's either positive or not. It's something that you can do numerically, it's something that you can do analytically. It's really a calculus problem. Quasiconvexity is a condition from a different world. This is an integral condition. You have to verify it for all functions. It essentially amounts to solving a minimization problem. So if the answer to Morrey's problem, if rampant convexity is positive, if rampant convexity implies quasiconvexity, this means that you can solve variational problems just by taking derivatives. You check some differential conditions. If they are met, then you can solve your problem. And this, of course, will have all kinds of implications. So, usually when something sounds too good to be true, it's because it is. And so this is what Faraco showed in 92. He showed that if the target, again, remember, we are looking at maps from Rn to Rm. And Faraco showed that if the target M is 3 or higher dimensional, then indeed, there are no miracles. And rampant convexity does not imply quasiconvexity. And there's a more recent example recently by Guerra, which takes even higher dimensional targets. So he takes 8 or higher dimensional targets. And the reason I mention these two examples is that they are essentially the only examples that are. There are no other examples really of the failure of this implication. So in particular, you see from here that the case where the target is just two-dimensional is open. No one knows the answer. And there's really some evidence which has been mounting through the years with works by many authors. I wrote them here semi-chronologically. So Walsh, Faraco, Muller, Daconia, Kirchheim, Ivanic, Astala, Sekahidi, Faraco, and many others. And there's really some evidence which suggests that the two-dimensional case is different. A superficial reason is that, when M is 2, R2 is C, and there are many things that become true in the complex plane which are not otherwise. And, in fact, in today's talk, we will always be talking about the case M is equal to N is equal to 2. So we are going to be looking at maps from the complex plane to the complex plane. Yeah, so actually, I can now tell you our main theorem. So here's the standard notation. We are taking 2x2 matrices with positive determinant. Okay, this is kind of the natural set in elasticity. And we are going to write Ka for the distortion of A. So this is again distortion of angles. This is the operator norm. So it's the operator norm squared over the determinant. So here's our theorem. This is joint work with Astala, Faraco, Koski, and Kristensen, forthcoming. And so let's take an energy as in this Neo-Hookean model that I showed you. So it's a term of the distortion plus a term of the Jacobian. And we don't assume anything except that we assume that this second term is convex. Okay? This is just our assumption. So for this class of energies, we can actually solve Morrey's problem. So first of all, we can show that Rankine convexity implies quasiconvexity. And in fact, as I said, it's not obvious for such energies that quasiconvexity implies kind of existent theorems. The reason is that, again, these energies are unbounded, so they do not satisfy any kinds of growth conditions. But okay, we can still prove that they are actually weak lower semi-continuous, so we can really prove existent theorems with them. So to be slightly more precise, what do I mean by weak lower semi-continuity? I mean, let's just take a very nice boundary data, and let's take a sequence with this boundary data, which converges weakly in W12. It has bounds, suitable bounds in the distortion. Then I can pass to the limit in the end. So the limit of the energies is really greater or equal than the energy of the limit. So it's what you need to apply the direct method of the calculus of variations. I don't know if anyone has questions at this point.
The KUJ is the distortion?
This is distortion, sorry. Yeah, so it's exactly what you get, plug A equals du, essentially. Yeah, right. I mean, I can write it here because it's going to appear a lot. So Ku is really du squared over the determinant of du. So this is a number which is always at least 1, and it's exactly 1 if the map is conformal. Okay, so this is a measure of distortions of angles. Yeah. So this is the main result. So okay, the purpose of my talk is really to give you an overview of how to prove this and of the main ingredients that we need and that some of the ideas that we introduce. So really there are 4 main ingredients that I want to talk about. In fact, there are 2 statements. There are 2 implications. The first implication is how do you solve Morrey's problem in this class? How do you prove that Rankine convexity implies quasiconvexity in this class? Okay, and the second statement is how do you go from quasiconvexity to weak lower semi-continuity without having growth conditions? So these are really 2 separate statements. So the first statement, there will be 2 ingredients, extremal integrands and the Burkholder function. The second statement, again, quasiconvexity implies weak lower semi-continuity. There are 2 more ingredients. At this point, these are just buzzwords. So we need some kind of strengthening the Jensen inequalities, and we'll use the Stoilow Factorization. I mean, these are just really buzzwords at this point. I will explain what they mean. So let's start with the first part. How do you solve Morrey's problem in this class of functions? How do you prove that Rankine convexity implies quasiconvexity? So the first idea is something that goes back to my first paper. So let's just talk a little bit about convex analysis. And in the plane, of course, you all know that if I give you a convex polygon, there's a notion of vertex. People also call it extreme point in convex analysis, and you know that the polygon is just the convex whole of the vertices. And this is true in general for extreme sets. For convex sets, there's a notion of extreme point, and the set is the convex whole of its extreme points. Okay, this is true for convex sets. And so what I proved in my first paper is essentially a version of that result for Rankine convex functions. So you can think about the cone of Rankine convex functions. This is a convex cone. It's a little bit more complicated than just a polygon because it's unbounded and okay, it's infinite dimensional. But essentially this result, by the way, is kind of called the Krein-Milman theorem. It tells you that the vertices are a very efficient way of representing a convex set, right? You just need to know the vertices and you know everything. And so in my first paper, I showed that there is a version of the Krein-Milman theorem for Rankine convex functions once you define extremality in the correct way. And this really tells you that if you want to understand Rankine convex functions, you should really look at the vertices, right? And in particular, if you can prove that rank 1 convexity implies quasiconvexity at the vertices, you can prove it for all points in the convex hull, which would be the inside of the polygon. So what is very nice about this class of functions, so this is an observation done by Voss, Martin, Giba, and Neff, is that if you give me a function in the class that I'm considering, if this function is rank 1 convex, then you can write it in the following way. So you can write it as a function g, which is polyconvex, I'll say what it means in a moment, plus a non-negative constant times a completely explicit function w, which is written here. So w is the distortion minus logarithm of the distortion plus logarithm of the determinant of a. So just recall that, in this context, polyconvexity just means that you can write your function as a convex function of a and of the determinant. So polyconvexity is very close to convexity. It's just, you take a convex function and you also allow convex terms of the determinant. So we saw that the determinant is quasi-convex. It's the most important quasi-convex function. So if you compose it with a convex function, it does not destroy anything. So you can think that for the purposes of this talk, polyconvexity is a class of functions that we understand completely. We can prove, they are trivially quasi-convex. They are weakly lower semi-continuous. Since, this was done by John Ball in the 70s. So for the purposes of what we want to do today, polyconvexity is a completely understood notion. And so what this result tells you is that, all functions in our class are equal to a polyconvex function. So they are equal to something you understand plus an explicit function w. Okay. And w is not polyconvex. So this you can see in the following way. So you take the limit as t goes to 0 of w of t times the identity. Okay, let's just compute it. W is here. So the distortion of t times the identity is just 1. Log of 1 is 0 plus log of t squared, right? So you get this. As you send t to 0, this becomes minus infinity. And actually, it's relatively easy to see that for polyconvex functions, this is always a finite number. So this cannot be polyconvex. So this proposition by Voss, Martin, Giba, Neff, I just want to emphasize it. It does not say that w is the only non-polyconvex function in the class. That's not the case. It is just saying that it's the only non-polyconvex extreme function in the class. So there are many others, actually. Essentially, if you take, for instance, uniform perturbations of w, they will not be polyconvex. So it's just saying that, you have many extreme points in this class, but the only one which is not polyconvex is w. Okay. So essentially, we only need to understand w. That's the beautiful thing in looking at extreme points. You've reduced understanding an infinite class of functions to understanding one function. Okay, so we have to understand this w, which looks very funny, right? I mean, all of these logarithms, what is this? So this is where the second ingredient comes in. So this is the Burkholder function. So you will have to, excuse me, I will have to go on a bit of a tangent to explain where w really comes from. So the Burkholder function is in some sense the most beautiful function that you can write in 2x2 matrices. It was found by Burkholder in 1984 in a completely different context. He was proving sharp martingale estimates. And it's again a completely explicit function which is parameterized by a number p, which is at least 2. Okay, so the function is the following: bp is p over 2 minus 1 times norm a squared minus p over 2 the determinant times norm of a to the p minus 2. Okay, so let me help you digest a little bit this definition. So you should really think that bp is like an LP version of the determinant. So first of all, let's just compute it at the identity. So at the identity, this is 1, the p over 2 cancels, you get minus 1. Okay. If I take p equals to 2, the first term dies, and this becomes 1, so I'm just left with minus the determinant. So it's really like a generalization of the determinant. It's p homogeneous, right? So again, this is clear. The norm is 2 homogeneous, the determinant is 2 homogeneous, this is p minus 2 homogeneous, okay. It's p homogeneous. It's isotropic, like the determinant. If I replace a with QAR, where Q and R are rotations, I get the same. Again, the norm and the determinant have these properties, so it is inherited. And of course, very importantly for us, it is rank 1 convex. So again, this was actually shown already in a different language by Burkholder in the 80s. So of course, once you see a rank 1 convex function in R2x2, you ask, is it quasi-convex? And this is what Ivanich did in the 90s, and he conjectured that indeed it is. So this is a famous open conjecture due to Ivanich. It has very deep connections with harmonic and complex analysis. I don't want to get into that. I just want to say that even solving Morrey's problem for this function, completely explicit, if you can show that it is quasi-convex, you have solved, long-standing problems in harmonic analysis. So it's, that's why Morrey's problem is, if it's true, it's so deep. It tells you that you can solve all of these conjectures at once for free just by taking some derivatives.
Do you have Burkholder function in higher dimensions?
You do actually, yeah. So this was
also related to the decomposition that you showed on the previous slide.
It is, yes, it is, yeah. So
I
Ivan,
heard something.
yeah. So there's a beautiful paper by Ivanich, of course, from 2001, Transactions of GMS, where he exactly generalizes. He understands how to generalize this and it's really beautiful. Yeah. I mean, since you ask, I can say briefly. I mean, the reason this is connected with the harmonic and complex analysis is that, in some sense, the Burkholder function is like a master function, which rules all sharp integrability properties of maps, of quasi-conformal maps, and and other kinds of maps. And I will try to make this slightly clearer in a moment. So I've now talked about the Burkholder function. So here's what we can prove for it. So this is joint work with Kristensen and also Astala, Faraco, Koski, and Kristensen. So we can essentially, well, we cannot solve Ivanich's conjecture, but we can solve it if we have a sign. So give me a map, which again has linear boundary values, and let's assume that BP of this map does not change sign, so it's either positive or negative. Okay, then we can prove the quasi-convexity inequality. So, of course, quite far from a solution to the conjecture, but it is what we can do. I would love to talk more about this, but I don't have time. So let me just say that there were earlier works by Astala, Ivanich, Prowse, and Saxman between 2012 and 2015. And they introduce a beautiful complex interpolation argument, which we can then combine with an extremality argument using Kristensen measures. So these are just some buzzwords. I don't really want to talk about this. I just want to say that for the Burkholder function, we can essentially prove quasi-convexity if we have a sign. Okay, so what does this have to do at all with what I was talking about before? So what is the connection of these objects with this function W that we want to understand? So in elasticity, it's useful to consider this involution, f hat, which is really looking at the energy of the inverse map. So f hat of A is equal to f of A inverse times the determinant. And the characteristic property of this, why do you look at this object? Well, if you give me map U with inverse V, then the F energy of U is really the F hat energy of V. Okay, I mean, this is, you have an inverse here, and then you have the term that you need to change variables. So this is just the change of variables formula. And so, of course, if I take hat, I get the same thing. And the nice thing about this operation is that it preserves Pauli, quasi, and Rankine convexity. But it's easy to see that it does not preserve convexity. So if I take f equals to 1, which of course is a convex function, I get the determinant, which is not convex. So again, convexity is just not the correct condition for vectorial problems. So, okay, so this is an operation. And now you can do the following. You have this one parameter family of Burkholder functions, so it's parameterized by P. And you can take its derivative at P equals 2, why not? And the nice thing is that if you write down the definition of the derivative as a limit, it's this guy. And the determinant is quasi-convex, as we saw. BP is also partially quasi-convex. You sum two quasi-convex functions, you get the quasi-convex function. So f is actually quasi-convex as well. And here it is written explicitly. You can calculate the limit. It's norm a squared minus 1 plus log norm squared times the determinant. And now this is where W comes in. So W is what you get when you pass to the inverse map up to N1. So you pass to the inverse map and you get W. Okay, so you have BP, you take a derivative at P equals 2, and you look at the inverse, and this is W. So that's why we are interested in the Burkholder function for the purposes of the. And so since we can prove that BP is partially quasi-convex, we have a similar result for W and F. So we can actually prove that for smooth diffeomorphisms, they are quasi-convex. So, these are just the quasi-convexity inequalities. I mean, the reason, our partial result is enough is that, of course, a smooth diffeomorphism, you have a sign on the Jacobian if you have a boundary condition. So that's where the sign condition comes from. Actually, for W, it's completely natural to look at diffeomorphisms. It's not even defined if the map is not really, it's not defined for matrices with negative determinant, let's say. So this is really what you expect. So this is, again, so this is essentially how you prove the first part, right? Remember, we have this class of functions. We reduced it to understanding one function. And then we realize that this function is connected to the Burkholder function, and we can prove quasiconvexity for you. So before I said that the Burkholder function is like a master function which rules the sharp integrability properties of mappings. And I want now to show you why. I mean, these inequalities, okay, they look very nice, but what do they mean? So let me show you what they mean. So these are really sharp versions of the results of Muller and also Pascal Oninen. So for instance, Muller showed in 1990 that if you give me a W1 to map with Jacobian non-negative, then there's a surprising higher integrability. So the determinant of the U, which you would expect to be in L1, since the U is just in L2, it's actually slightly better. It's in L log L. Okay, so now you can ask, can you make this precise? And this is actually, the first inequality for F is doing exactly that. So let me write explicitly the first inequality. I mean, remember that F, it has this norm term, it has log squared the determinant, so it looks already kind of like L log L. And if you rewrite this explicitly, this is what you get. You get the determinant of du times log of du squared is bounded by the W1 to norm with constant 1 plus a boundary term. And this inequality is sharp. So this is a time with equality for many maps. So this is really, this is why quasiconvexity is difficult. You have to find sharp constants in all of these integral estimates. And okay, W has a similar interpretation in terms of inverse mappings. Yeah, so I don't know if there are any questions. If not, so if not, okay, this essentially solves the first part of explains how to prove the first part of the theorem. So let me talk now a little bit about the second part. So how do we go from quasiconvexity to weak lower semi-continuity, right? I mean, maybe let me go back just to the theorem to remind you. Right, so we had these two implications. The first implication is Riemann convexity implies quasiconvexity. This is what we saw. Now we want to prove some weak lower semi-continuity results of this form, right? So we have weak convergence in W12. We have bounds on the distortion, and we want to show that the limit of the energies is greater than the energy in the limit. Yeah. So how do we do this? So again, this is where complex analysis is again kicks in with all its strength. So we want to look at what people in complex analysis call principal maps. So a map from the complex plane to the complex plane is a principal map if it's holomorphic outside the unit disk. So z larger than 1, it's a holomorphic function. It's kind of the identity at infinity, and then it has this Lohan series. So there's no zeroth order term if you want, and okay, there's also no higher order term. So it's a map. Essentially, you should think of it as a map which is the identity at infinity, and it's holomorphic, so it has some extra terms. Why do we care about these maps? So an important thing to realize is that this essentially generalizes maps which are linear on the circle. And the reason is the following. I mean, let's just take, without loss of generality, let's just take a linear map for which the conformal part is just the identity. So it's a map of the form z plus b1 times z bar. Okay, this is a linear map up to multiplying by if it is any linear map in the complex plane, you can write it like this, up to multiplying by some complex number, which is kind of irrelevant for this discussion. So let's just take it to b1. So you take a map like this, and now if you are on the circle, of course, z bar is just 1 over z. So on the circle, this map agrees with the first two terms in this expansion. So essentially, if you have a map which is principal, okay, and for which all of the coefficients starting at j equals to are 0, so the map is literally z plus b1 over z, you can think of this map as a map which is actually linear on the circle, right? It agrees with the linear map there. In general, it's a larger class of maps because there are more coefficients, so you cannot really do this trick to all of them. You can just do to the first two. And so in general, you should think that this is a much larger class of maps. But it essentially includes maps which are linear on the circle. Yeah, so So here's what we can show. So we can show a Jensen inequality for W for these maps. Okay, so remember that, I mean, let me explain. So for quasiconvexity, right, we defined it as you have a Jensen. So we saw that quasiconvexity of F is really a Jensen inequality for gradients of this form, right? This is one way you can write quasiconvexity. But okay, what is U, right? We saw that U should be a map of the form A plus C infinity C. So it's a map which is linear on the boundary. These maps are not linear on the boundary anymore, right? They can be if all of the other coefficients are 0. But in general, they are not. They have more terms. So this is what I would call in this talk Jensen inequality for principal maps. So it includes the standard Jensen inequality where you test with linear boundary values, but it's more general. It allows a larger class of maps which are holomorphic outside. So we were pretty surprised with this. We had never seen, I mean, we didn't know that this could really happen. And so I just want to tell you more or less why it happens. Why can it happen? Because it's actually relatively easy to see. So let's just take, for our own sanity, let's just take V1 to be 0. Okay, this will make our life much easier. If V1 is 0, you can compute this integral and it's just going to be the identity. Okay, so what you really want to show when V1 is 0 is that W of the identity is less or equal than the average of W of the U over the disk, right? This is just the same inequality when this is the identity, okay? And again, recall the definition of W. It's a distortion minus log of the distortion plus log of the determinant. So I've already tried to convince you that W is quasi-convex. So what this means is that, so let's just look again what a principal map is, right? A principal map is a map which is the identity at infinity. Okay, if it's the identity at infinity, this essentially means that you are in this class, right? It's a linear map plus, okay, it's not a compactly supported function, but it's a holomorphic function which decays very fast, so it's the same. So really, you already know that when you are in the full complex plane, W of the U minus W of the identity is non-negative. This is just quasi-convexity. Maybe I can raise it slightly. This is just what the quasi-convexity inequality tells you. You have a map U which agrees with the identity at infinity. Okay, this is the Jensen inequality for, this is just the definition of quasi-convexity, which we saw how to prove it, more or less. So what you need to understand if you want to prove this? Well, you need to understand what happens in the complement of the disk, right? Let's see what happens at the integral in the complement of the disk. And for this, there's nothing like calculating explicitly. So let's just call C this difference. And let's calculate explicitly. So if the map is holomorphic, the distortion is 1. So you get 1 minus 0 plus log of the... So if a map is holomorphic also, I mean, remember, so being holomorphic means that this is equal to 1. So it means that the determinant is equal to the norm squared. And so you get 1 plus log of the norm squared. W of the identity is 1, so the 1's cancel, and you are just left with this term. But U is holomorphic, so this is a harmonic function, actually. And now, you see, what this means is that your integrand here is really a harmonic function outside the unit disk. And harmonic functions are very nice. So you should think that you can apply the mean value theorem at infinity. So at infinity, this is a function which decays. Again, remember that U prime, so U of Z was like Z plus, so the first coefficient was 0, so B2 of Z squared plus other coefficients. So U prime of Z is 1 minus O of Z to the minus 3. So this is a harmonic function, which is approximately 1. So U prime is approximately 1 at infinity, which means that psi is approximately 0 at infinity. So just apply the mean value theorem at infinity. 0 is the value at infinity. And now if you think about, if you are in the Riemann sphere, right, you think about infinity, you think about balls centered around infinity, this will give you exactly the complement of the disk. If you want to make this precise, okay, take an inversion, map it to the unit disk. So the integral is really 0. So psi integrates to 0. People in the theory of null quadrature, so this is called a null quadrature domain. The domains with the property that harmonic functions integrate to 0 on them, and they have been completely classified by Sakai. So we have the first inequality, which is just quasiconvexity. Okay, and this just tells you that actually the integral is 0 outside the disk, so there's no contribution, and this is how you get this inequality. So the fact is that W, this difference is a harmonic function outside the disk, so it's quite special. So this is essentially why you can get this kind of Jensen inequalities without linear boundary conditions. In general, if you have, so I said, okay, let's set B1 to be 0. Why is this good? I mean, the first coefficient is 1 over z, which decays a bit too slowly. So in the general case, you have to make some change of variables, and really here, when you do this change of variables, here it will appear the complement of an ellipse instead of the complement of a disk. The ellipse is, so you should think the disk is the image of the disk by the linear map, which is the identity. In general, it will be an ellipse, which is the form, according to B1. But okay, complements of ellipses still have this property, so you can still run the proof. Right, so this is the third ingredient. You have this very strong quasiconvexity inequality. So now, and to get to the end, let me try to explain why we care so much about principal maps and about these strong quasiconvexity inequalities. A difficulty in all of these problems is that you have a constraint which is non-convex. You have a constraint on the Jacobian. The Jacobian has to be positive. So it's not clear how to, the usual arguments that one takes with cutoffs and these kind of things do not work. So what works here are instead topological arguments, which are very two-dimensional. So remember that we wanted to prove a weak lower semi-continuity result for our class, and we saw that all functions in our class can be written as W plus polyconvex functions. Polyconvex functions we understand very well. We can prove lower semi-continuity theorems for them. So it suffices again to understand W. So this is what we really want to show. We have a sequence again with nice boundary conditions. It converges weakly in W12, bound on distortion. The limit of the energies bounds the energy of the limit. Okay. So to do this, we will need our strong Jensen inequalities. So let me give you a rough sketch of how this goes. So the first thing that you can do in this kind of problems is to apply the theory of gain measures. So it's not so important what they are if you're not familiar with them. You can just think of them as a tool that essentially allows you to reduce to the case where the whole sequence, instead of converging to some map U, converges to a linear map. Okay, essentially you can take the limit to be linear at the cost of losing maybe the boundary conditions. Okay, the boundary conditions get lost once you do that, but the limit is a linear map, which is very helpful. So what do you want to do? Well, you want to replace your sequence of maps, which is converging weakly to the identity. You want to replace it with a better sequence to which you can apply quasiconvexity. Well, what should this sequence be? It should be a sequence of principal maps. That's what we just saw. So in this setting, we have a beautiful result by Ivanic and Faraco, where they show that what is known as Stoilow Factorization still holds in this setting. So the Stoilow Factorization says the following. You give me a map which is open and discrete. This map is topologically a holomorphic function. So you can write it as a holomorphic function composed with a homomorphism, Fj, which is a principal map. So in fact, topologically just says that, in the general setting, it just says that any open and discrete map can be written as a holomorphic function composed with a homomorphism. In this setting, you can say more because you are assuming more things. And so what Ivanic and Faraco shows is that you have this topological result still here. So you can write your maps Uj as holomorphic functions composed with Fjs. So the Fjs are principal maps. They are, again, they're going to be holomorphic outside the unit disk with these asymptotics that we saw here. Z plus B1 over Z plus B2 over Z squared and so on. So, okay, now you have this sequence Uj, which you write it in this way. The sequence is bounded in W12. you need to control the holomorphic factors. Okay, this is relatively easy to do. There are holomorphic functions in the end. The sequence is converging weakly to the identity, so you can actually see that the holomorphic factors have to converge to the identity themselves. Once you have bounds in the holomorphic factors in whatever space, you get bounds in infinity, right? So in some sense, you have, these are estimates that you have to do, but you can, I mean, you essentially can control these guys in all norms that you like. So what does this mean? It means that, again, you want to look at the limit of the W energy of Uj, and it suffices to look at the limit of the energy of the Fj, where Fj are now principal maps. You can just, you know, cut off these Hj. You don't really need to care about it. But now you are in good shape, because you see these are now principal maps, and we have proved Jensen inequality for them. So the Jensen inequality is just this last inequality. This is exactly what you wanted to do. So you have showed lower semi-continuity. This is why you need the Jensen inequality for principal maps. And it's really important that you have it. I mean, you see, there's no way that these maps will be linear on the boundary conditions, because, right, they are, I mean, there's just no way. It would have to be incredibly rigid. I mean, once you know, if they are linear on the boundary, since they are holomorphic, they are linear throughout the complex plane. All of the coefficients are zero. Once you apply these Stoilow factorization, there's just no way that you will have boundary information on the map Fj. So you really need a Jensen inequality that allows for that, and that's why we need these Jensen inequalities. Okay, so this is kind of the end of the overview of the proof, and that's what I wanted to say. So thanks for your attention, and